In this video, I'm going to talk about communication. There are various forms of communication. We have chip to chip, chip to computer, and chip to device. But most likely this device is probably just some form of another chip. Specifically in this video, we'll be talking about chip to chip communication. And the form of communication we'll be talking about is UART, which means universal, asynchronous, receiver transmitter. There are many other forms of communication, but we won't be getting to those in this video. It's one of them is I2C and SPI. They all have similarities, but the UART is actually quite a bit different in the way that it communicates using an agreed upon timing. And these have to use a clock source, and we'll get more into that when we get into these videos. You may not have heard of UART before, but if you've used computers for a while, you probably know of RS-232, and you may not know of this one, but this another one is RS-485. And this is generally used, the RS-232, in the case of communicating from chip to computer. RS-45 is generally used for chip-to-chip communication, but we don't really need to understand what these are. We're just going to get into the nuts and bolts of actually making the UART work. The chips, or the microcontrollers, need to have a way to talk to each other. So they need a way to speak and hear. And to make AVR1 and AVR2 talk, one has to be talking. So there are actually these pins on the microcontroller that will talk. And you'll have a pin that listens. This pin is called TX. So we're going to call him Mr. TX. And this pin is called RX. So we'll call this pin Mr. RX. And TX, obviously, you know that means transmit, and RX obviously means receive. So when we're listening, we have the ear here. It's listening to the other one talk. Let's go ahead and show that on the other chip. So this would be TX on this side and RX on this side. And one of the most important things we have to take into consideration is the speed at which one is talking and the other one is listening. And you know, I've heard New Yorkers talk really fast, so let's pretend this is a New Yorker. Not really. I don't really know if that's true, but let's pretend this guy is from New York here, and this Mr. RX is from, I don't know, Hawaii. Mr. TX over here from New York is going to be talking way too fast, kind of like how I'm talking right now, to this ear in Hawaii, because he likes to relax, and you know, he takes a little while to talk and to listen. But this, in terms of chips and this method of communication, this would be a problem, because the RX on this side needs to be able to listen to the TX on this side at the exact same speed. And that is also true for the TX on this side. And this is Hawaii here. And the RX on this side, this one's from New York. And this one's talking way too slow for the New York one to understand. He can only understand fast talk. So we're gonna need both of these to be talking at the same speed. And speed in the UART world is called baud. This is the baud rate. A lot of the younger folks out there may not even know what baud is. This could be a term that is very foreign to youngsters, because in computers these days we don't actually use baud anymore, because we don't do much serial processing with computers. It's mainly all networked with network cables and Ethernet and whatever. Even though those do have a speed, it's not considered baud. But we have to go back and go back to the idea of baud in this case. And all you have to know, it's just a speed. It's a frequency at which these two will listen and talk. So they are listening at the same rate of speed as the other one is talking. The asynchronous term used in UART really just means that we're going to be using a baud rate agreed upon speed rather than a clock source or a wire that has a sort of heartbeat to it that everybody uses as its clock source. There are two ways of providing this communication. One is called half-duplex and the other one is called full duplex. In half-duplex, the two chips, let's see, the RX and the TX, see TX here, and RX, communication can only happen at one time. Communication can only happen in one way at a time. So either the TX and this RX is communicating, or this TX and RX is communicating. This is half-duplex. You can see that really only one line is necessary in this scenario. So this is one way you can sort of get away with using fewer wires in this communication if you need it. Sometimes it is unavoidable. You don't have the choice whether you can work in half-duplex or full duplex, like in some devices such as this servo. This servo only has 3 pins. One is for ground, one is for power, and the other one is for the communication. And this is a digital servo, so it actually uses a UART communication form to be able to turn the horn here. It has an ID. Let me see where the ID is. Yeah, I haven't assigned this ID yet, but I can assign this an ID, and I can tell this particular servo over a line of a whole bunch of servos, this is the one that I need to talk to, and this is the one that needs to perform the task that I give it from the microcontroller. Inside of this is actually another microcontroller, and I believe it's maybe an Atmel AVR microcontroller. I think it is. And connecting this to the AVR chip, this would be similar to a chip-to-chip communication, but it looks like it's a chip-to-device communication. And that's why earlier I said that it may appear to be a chip-to-device, but really it is a chip-to-chip communication. It's just disguised by its form. And I just alluded to a specific type of communication that you can have multiple communication recipients and talkers, I guess you'd call it. So in this example that what we're talking about with the servo, you can have your main chip here, the AVR, and you have the TX and RX. And there is actually another chip that is going to go between this, but I'm just going to be, for the sake of simplicity, just going to call it one line going out. So these two are actually connected together in some way. There will be a chip actually in the middle here, and we'll get into that a little bit later once we get into this other form of half-duplex communication. But in this form, you could actually, like in these servos, let's make this a long line here. Let's put a servo on the end. I'm just going to draw it as a chip because really it is just a chip. And inside of this servo, it actually has a TX and RX, but we'll just show one line coming out, and then you have another, and then you have another one. So you can have as many as, I believe, I can't remember, I think it's maybe 128 or 255 servos on one line. Let's put one on this side. So this is serving as an example of half-duplex. And let's say my AVR says, okay, I want, let's put numbers here. Let's say I want servo number 3. So I send out some form of communication we really haven't talked about yet, but some form of communication out in this direction, saying Mr. number 3, ID number 3, it's going to pass through each one of these. It's going to go inside here, and say, am I number 3? No, I'm not number 3. So it's going to go over here and say, am I number 3? No, this is number 3. I'm going to reject it, continue going. Is this number 3? Yes, this is number 3. So I'm going to accept whatever instruction that this has to give it. And number 3 will perform the instruction, and maybe number 3 will pass back some information in this direction to state whether it was able to achieve that or it failed the instruction. So you have both forms of communication going on one line. Now the difficult part here is to determine whether we are talking or listening on the line at any specific time. So you can tell the AVR, okay, I'm going to wait until I receive all of the information from all of these servos, and once I'm done with that, I'm going to go ahead and send the next instruction. This was just sort of a small introduction to half-duplex. We're going to get into this in a later video. This particular video, we're going to be talking about full duplex. So let's take a look at the full duplex. And this essentially is full duplex operation. We are talking and listening at the same time. So let me write full duplex. And we don't need that Hawaii anymore in New York, so well, I'll keep it in there just for. I'm going to go ahead and remove it. I need better erasers. So full duplex, the communication on both lines can happen at the same time. The next important thing to understand is that these folks over here, when they're talking, they have to talk in short blocks. Or sentences. We'll call it sentences. And just like in English grammar or whatever, maybe other forms of grammar, you'll have a sentence. Let's write the sentence here. Let's say, do this. And we generally have a period afterwards. So this is do this with a period. In the UART communication, this is called a stop bit. These are called the data bits. And there's also something in the beginning called a start bit. But we're not going to be talking like regular sentences. These have to be on-off bits. This is kind of like when we were in school and we're doing like these secret codes where you'd have to figure out a sentence from looking at some kind of encryption, sort of a guide or a key on the bottom that changed all the nonsensical information to something that makes sense. And so, like I said before, we have our stop bit. Let's just call that let's put a box here. That's a bit. And we know what bits are. They're just ones and zeros. And then we have some number of data bits. I'm going to put one. Oh no, let me put that on the bottom. Let's say the one data bit. Let's see, number 2 data bit, number 3 data bit, number 4 data bit, number 5 data bit, number 6 data bit, and number 7 data bit, and like we usually have, or a good uniform number of bits would be 8, sort of 0 to 7, or index 0 to 7, 1 through 8 data bits. We can have different lengths of data bits depending on what kind of communication we would like to send, what depth of communication we would like to send. And then we have the stop bit. And I'm going to call this the stop. And then we have over here the start. And this entire set of bits is called the frame. These, like I said before, are called the data bits. And just like the baud, both of them have to sort of speak at the same language. They have to, or speak at the same speed using the Baud rate. And they also have to both acknowledge the frame size, number of data bits. There's also, on the end, it could be a parity bit. Sometimes that's used in 10-bit communication. And that could be either odd or even. We'll get into that a little bit later. But both microcontrollers must agree to the same specifics, like I'm going to have a start bit, I'm going to have a stop bit, and I'm going to have 8 data bits between the stop bit and start bit, and I'm going to be running at this particular baud rate. So those are sort of things that both of them have to agree on. If you said, like on this side, I'm going to be sending 9 bits instead of 8 bits, but on over here I'm going to be sending or receiving 8 bits, then this microcontroller will not understand what this one is saying, and this microcontroller will not understand what this one is saying. So it's really important to have the frame to be equal, the frame characteristics or attributes to be equal with both of the microcontrollers. The parity bit that was mentioned before is really just to check to see if this has any errors or not. So let's pretend we have a combination of zeros and ones. Let's say 1 0 0 1 0 0 0 1. So let's say that is the data that we're sending, and that's what we want the other microcontroller to understand or to receive. Maybe sometimes this data is going to become corrupt, or there's going to be interference coming into this particular wire at the time of communication. It needs to sort of have some way of determining whether this is valid or not. And this is a really, really sort of simple way of error detecting. It's called the parity bit. There are 2 ways you can set the parity bit in the microcontroller, and you can set it to be even parity or odd parity. And in the, let's say we set the parity bit to even parity. And if it's set to even parity, that means that the bits within the data bits, the ones with the ones, would have to add up to an odd number because it includes the parity bit to make it an even parity. Or let's say this would be equal to 3, so 1, 2, 3. So there's an odd. This would be odd. 3 is equal to odd, but counting the parity bit, that would be 4. So the parity bit would be a 1. If this was an even number inside, not including the parity bit, that means with the parity bit it would be odd. So let's say there was a 4 inside the data bits, and you add the 1 for the parity, that would be 5. So that would be odd. So that would be a 0. The parity bit would be a 0. And you can have the same thing with odd parity set. So it would be the same thing if the number of ones equal an even number, and then you add the 1 for the parity. Let's say that was 5 with the parity, then that would be a 1 because you set it in the microcontroller as odd parity. And then if it came up with an even number including the parity bit, then it would be a 0. So let's look at an example of how parity works. Let's draw a couple microcontrollers. Okay, so if we wanted to send over, let's say 8 bits, but I'm gonna do a couple ones and zeros here. This would be my transmission data bits from this microcontroller to this microcontroller. This is what I want to send from number 1 to number 2. So let's say we set the parity to even on both sides. So let's say, Mr. Number 1, I'm going to set you to even, and I'm going to set you over here to even as well. In this example, we won't talk about the start bit and end bit, just the parity example. So since this is an even number, we're going to have to put another 0 after this, because this is the parity bit. And like we said before, if this is set for even, that means that the number including the parity bit would have to be even. So that means this has to be a 0, because if I put a 1 here, then that means it would be an odd number. So when this gets to the destination microcontroller, this better have a 0 at the end, and this better have only 2 1s here. So if it doesn't, if it has like 3 1s here, and this was 0, then we know that we have a problem, because this is set at even, unless this was set incorrectly at odd, and then we would have problems on every single transmission except for the ones that were actually bad. Let's do the same thing for odd parity. So let's draw our 2 microcontrollers again. So this is number 1, and this is number 2. So let's set this one to odd, and set this one to odd. And we'll transfer from 1 to 2 again. So let's put in an even number. 0, 1, 0, 0, 1, 0, 1, 1, 5, 6, 7, 8. Okay, that's good. So we have 1, 2, 3, 4. We have an even number of 1s in here. So the parity bit would have to be a 1 because we have set it to odd parity. So this odd parity transmitter will be adding a 1 at the end because it needs to be an odd number of 1s totally. And then when it gets here, this better have a 1 on the end, and there better be an even number of 1s in the data bit to be a successful communication. Of course, this isn't perfect error checking. Obviously, you could add a couple more 1s in here, and then you still have the wrong answer. But it is some form of error checking, and it's better than nothing. Actually, let's do another odd so you can see the other, putting a 0 there. So if there was an odd number, 0, 0, 1, 0, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there is already an odd number within the data bits, so we better put a 0 at the end because we want to maintain an odd number at the parity. So the transmitter will set that parity bit, and then the receiver will just make sure that that is a 0, and it'll check with the number of 1s in here because it's set it odd, and it's counted 3 1s. That's odd. This is a 1. It looks like a 7, but it's a 1. So it's counted 3 1s, and yes, sure enough, it is odd. Let's look at the other case of even again, just to sort of wrap it up. So these are set at even, and let's put in an odd number of 1s in here. 1, 0, 0, 1, 0, 1, 0, 0. That's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so since there's an odd number of 1s in here, we better put a 1 here to make it an even number overall. And then over here, this is the transmitter putting this in. Over here, this microcontroller is going to check to make sure that there is an even number of 1s in here. And if there isn't, that means that there is a problem, because let's say there's a 1 in here. Somewhere in the communication line between these two microcontrollers, and a 1 was added somehow because of some interference from a motor nearby or something, caused a 1 to be here. Then that means that there is a 1, 2, 3, 4, 5 1s in here, but this is set at even, so that means that this must be incorrect. And then since the error checking is happening, this microcontroller has to resend the information. We have to make sure that this microcontroller got it right or got it wrong, or received the correct or incorrect information. And if it received incorrect information, it really does have to sort of inform the first one that was incorrect, and please send another communication so it can be correct. It is, of course, your decision whether you want to use a parity bit or not. You may not. You may have a pretty robust system and not need the parity because you are pretty confident that there won't be any errors coming through the data line. So you can use it or you can not use it. So you have that option. Okay, in the next video, this is actually concluding this video. We have a pretty good understanding of the UART functions and the features and how you set things. We didn't go very deep into the baud rate setting, but we really can't really do much until we actually sit down and look at the data sheet and start to program the microcontroller and set up our circuit. So in the next video, we're going to actually get our hands dirty and set up a circuit on our breadboard, and we will start writing the program to communicate from one chip to another. So in review, we've looked at the understanding of there are 3 different types of communication. There's chip to chip, chip to computer, and then chip to device, which is really just chip to chip. We understand the UART idea and how it is used between the 2 chips. We have chips talking to another chip that's listening, and we have another chip that's talking, or the same chip that's talking back to the the source chip, which is listening. And we understand that that is full duplex communication. We also know that there is a method of half duplex, which we'll get into in a future video. Half duplex, we can set up all kinds of scenarios, which create a single line type of communication with many devices on that line. And we could do that with full duplex as well. We can do the same thing. We can set up many devices on one line, as long as we understand which device we'll be talking to and which one has the appropriate ID being talked to. We understand the frame of the data being sent. The frame consists of a start bit. We have the data bits, which is it's your choice between 7, 8, 9, 10, and sometimes the 10 is actually the 10th is the parity bit. But we also have the option of putting a parity bit after the last data bit, and then we have a stop bit to inform that that is our period or the end of our sentence. And then we also understand how parity works, and why parity is used as for error checking, and how the bits are set up in parity communication. Thank you for watching. If you are following along with these experiments or producing successful projects on your own, helped by these tutorials, please let me know using the Contact Us page on the newbiehack.com website. I would like to feature these on the website to benefit and motivate others to join this creative field. Thank you.